Assalamualaikum. Let's start this lecture. Last lecture that we were doing about the modulation, and we covered 16 QM. After that, we have probability of error and bit error rate. So probability of error and bit error rate are often used interchangeably, although in practice they do have slightly different meanings. So probability of error and bit error rate are these are two terms that we use often interchangeably, but probability of error is something that we calculate before implementing the system. So it's kind of theoretical bit error rate that we are expecting. Uh, our expectations about the bit error rate is your probability of error. So that probability of error that is your value that you are expecting that this will be the bit error rate after implementing the system. Whereas bit error rate is something that is the actual historical record of system's actual bit error rate performance. So BER is the actual value that you will receive after implementing the system, or you will experience, or you will measure that bit error rate. And probability of error is something that you assume that or you will expect that a system will have that value in terms of bit error rate. So a bit error rate is made and then compared with the expected probability of error to evaluate a system's performance. Means if your PE, that is the probability of error, is equal to bit error rate, that means your system is performing according to your expectations. The performance of the system is better. But if the BER is greater than the PE, that means the system performance is not up to the mark or up to the expectation that we have set. So probability of error is a function of the carrier to noise power ratio, or more specifically, the average energy per bit to noise power density and the number of possible encoding conditions if you use the M array modulation schemes. So carrier to noise power ratio is the ratio of the average carrier power, the combined power of the carrier and its associated sidebands, to the thermal noise power, and can be stated in watts or dBm, where that you can see that is the carrier power that is given as C. In dBm, it will be equal to 10 log of carrier power in watts divided by 0.001. 0.001 because we are calculating this carrier that is given in watts, but we are converting it in dBm. So dB, to convert anything into dB, we use 10 log and that quantity, but we are converting it into dBm. So we have to divide that by 10 power minus 3, that is 0.001. Whereas the thermal noise power is expressed mathematically as N is equal to KTB. Again, that is power, so unit will be watts, where K is your Boltzmann proportionality constant, and that is equal to 1.38 into 10 power minus 23 joules per Kelvin. And temperature is your Kelvin, and room temperature will be equal to 290. And bandwidth is in hertz. So again, if you convert that same in dBm, you have to multiply that with 10 log and divide it by 0.001, that is 10 power minus 3. If you want to convert the given power in watts into dBm. So this probability of error, we say that is the ratio between carrier to noise power ratio. So we can write C over N, and that will be equal to C over KTB. That will be a unitless ratio because both have the same units, so those will be cancelled, and you will have a unitless ratio, that is C over KTB, where C is carrier power in watts and N is the noise power again in watts. You can also convert that into dB by multiplying C over N by train log, or you can rewrite that into dBm by having C dBm minus N dBm, because in logarithm your dVn will come as the subtraction. So you can also write this C over N is equal to C over KTB and dBm scale using equation 32. On the other hand, we have energy per bit. It's simply the energy of a single bit of information, how much energy consumed by a single bit when it is transmitted. So mathematically, it is given by equation 33. That is energy per bit is equal to carrier power into TB, that is the time of single bit. So when you multiply total carrier power with the time of a single bit, you will get the energy per bit. So that you can also write in dBj. J is here a joule. Then you multiply 10 log of EB, that is equation 34, that will give you energy into decibel joule. And because time of single bit is also given as 1 over f of b, where f of b is the bit rate in bits per second. So EB can be written as C over f of b. So instead of T of b, we can replace T of b by 1 over f of b. So there will be uh, energy per bit, that is joule per bit, that will be C over f of b, where C is your watts and f of b is your bits per second. You can also write that in dB by equation 36 by multiplying it by 10 log of C over f of b, or removing the dVn by the subtraction in logarithm scale, that will be log 10 log of C minus 10 log of f of b. So that is equal to energy per bit in decibel. So noise power density, that is the third term, noise power density, means how much power we have in a particular frequency. So that is uh, watts per hertz, that is power per frequency, that we say power density. In a particular frequency, what is the strength of noise? So that is determined by this noise power density. That is your thermal noise power normalized to 1 hertz. How much you have power density, how strong your power is in 1 hertz, that is determined by noise power density, and it is given by N over B, where N is noise and B is your bandwidth. You can replace to the normalized value, then N naught will be equal to N if B is your 1 hertz. So in this equation 38, N naught is your noise power density, that is watts per hertz, N is thermal noise power, and B is your bandwidth in hertz. So you can also write that in dBm by multiplying N by 10 log and divided by 0.001 and minus 10 log of B. So uh, equation 38 can be stated in dBm, n in dBm, while bandwidth is in dB, that is 10 log B. So in dB scale, it will be dBm minus 10 log of B. So combining equation 29 and 38, equation 29 is your n is equal to KTB. So we have B here. So equation 29 also is n, and equation 38 is also uh, n naught. So we combine them, we will have this n naught will be equal to KTB and by n. So instead of n, we put its value, that is KTB. So B bandwidth will be cancelled out and n naught will be equal to KT, that is watts per hertz. And that can also be stated in dBm scale by 10 log K over 0.001 plus 10 log of T. So energy per bit to noise power density ratio is used to compare two or more digital modulation systems that use different transmission rates, modulation schemes, or encoding techniques. The energy per bit to noise power density ratio is simply the ratio of energy of a single bit to the noise power present in 1/3 of bandwidth. So normally we have signal to noise ratio, that is in analog, the metric is signal to noise ratio, where we compare the power of the signal to the noise. But here we have this energy per bit to noise ratio. So when we transmit more number of bits in a single symbol, so EBN naught will reduce. So the energy per bit will reduce with respect to noise, and so as the chances of having more bit error rate in high order modulation schemes are more compared to low order modulation schemes, because low order modulation schemes have higher EBA naught compared to high order modulation schemes. So thus EBA naught normalizes all multi-phase modulation schemes to a common noise bandwidth, allowing for a simpler and more accurate comparison of their bit of their error performance. Mathematically, EBA naught is C divided by f of b, n over b, c b n f of b, where EBA naught is the energy per bit to noise power density ratio. Rearranging equation 43 is the following expression, that is 44 and 45 and 46 can be given as uh, energy bit to noise ratio, that is 10 log of EB minus 10 log of N log. So that will give you the how much energy consumed in one bit and how much noise spectral density we have in 1 hertz. Our noise density we have in 1 hertz. So from equation 44, it can be seen that EB/R ratio is simply the product of the carrier to noise power ratio and the noise bandwidth to bit ratio, rate ratio. Also from equation 44, it can be seen that when the bandwidth equals to bit rate and EB/R over C over N. So the bit error rate performance for the various multi-phase digital modulation systems is directly related to the distance between points on a single state space diagram. For example, on the single state space diagram for BPSK shown in figure 47a, it can be seen that the two signal points, that is logic 1 and logic 0, have maximum separation, that is maximum separation in distance for a given power level is D. So 47A. So that is your 47A. You can see we have two logics. At 180 degrees, we have logic 0, and we have 0 degrees. At 0 degrees, we have logic 1. And the maximum distance between these 2 points is d, and from the threshold point, the maximum distance is d. So that is how the 2 points are separated from each other. And so when so that means we have still have in terms of degrees, we have 90 degrees of, you can say, the uh, leverage or the tendency to move in from 0 to 90, or in between. If there is any change in angle degrees of this logic 1, it wouldn't be in the error region. Means error happen when we assume logic 1 as logic 0, or we receive logic 1 as logic 0. So the difference between the error logic and the actual value is in terms of degrees is 90 degrees. So we have a space of 90 degrees to move in before we enter into the error region. Same as for the logic 0. It has 90 degrees before it enter into the error region. So we call these threshold points on either side, as you can see. Whereas one BPSK signal state is the exact negative of the other, as the figure shows. A noise vector Vn, when combined with the signal vector Vs, effectively shifts the phase of the signaling element Vse alpha degrees. If the phase shift exceeds So for BPSK, it would require a noise vector of sufficient amplitude and phase to produce more than a 90 degrees phase shift in the signaling element to produce an error. So see, we need a vector that will produce this 90 degrees phase shift so that it can enter into the error region. So for PSK system, the general formula for the threshold points on a signal state space diagram for PSK, uh, that formula is given by, so that is sine theta is equal to sine 260 divided by 2m. That is g over 2 and divided by d. That is equation 48. That will determine the uh, formula for the distance formula for the when you rearrange equation 48, you will have equation 49. From there, you can calculate the d, where you have to put m, that is number of phases. For BPSK, for example, this will be equal to 2. So that is 2 sine 180 divided by 2. So that is 90, and sine 90 is equal to 1. And that will be d is equal to 2 of d. That is very obvious from the 2 is equal, d is equal to of d. That is d is equal to 2 of d. That is the, and d will be equal to d by 2. So that is the maximum distance that one need to be in the error region. So that you can determine from that formula of 49. So see now here we have this uh, PSK, 4 PSK, where we have 4 vectors, 00, 10, 11, and 01. So now the distance between the two vectors is d, and one needs d over 2 distance to be in the error region. So like this one, VS11. So this error region for 11 state, so that means you have to move all the way plus 45 and another 45, that is 90. So you can be here in this error region. So for 11 to be 10, it should be in this region. Similarly, for 10 to be 00, it should be in this region. And that is how we can calculate the distance of this particular error region. So 47b shows the signal state diagram for a QPSK, that is 4 PSK. You can see from figure 47 and equation 48, it can be seen that QPSK can tolerate only a 45 degrees phase shift. So from equation 47, the maximum phase shift for 8 PSK and 16 PSK is 22.5 degrees and 11.25 degrees respectively. Consequently, the higher levels of modulation, that is the greater the value of M, require a greater energy per bit to noise power density ratio to reduce the effect of noise interference. Hence, the higher the level of modulation, the smaller the angular separation between signal points and the smaller the error distance. So the general expression for the bit error rate, bit error probability of an M phase PSK system is given by equation 50, where ERFC is the complementary error function and is given by this Z sine pi by M log of 2M square root and square root EPM naught. So by substituting in equation 50, it can be shown that QPSK provides the same error performance as BPSK. This because the 3 dB reduction in error distance for QPSK is offset by a 3 dB decrease in its bandwidth. So in addition to the error distance, the relative weights of the noise bandwidth must also be considered. So when you have BPSK and QPSK, so the error rate performance is similar because one has 90 degrees threshold, one has 45 degrees. But the problem is BPSK need more bandwidth, or you can say the twice of the bandwidth to that of the QPSK. So QPSK will offset that 45 degrees less margin by this 3 dB decrease in its bandwidth. So that's both systems provide optimum performance Whereas figure 48 shows the error performance for 2, 4, 8, 16, and 32 PSK system as a function of EBA naught. So that you can see uh, probability of error against the EBA naught. So we have 2, 4, that is BPSK and QPSK, that is 8 PSK, 16 PSK, and 32 PSK. So see the power as we increase the uh, EBA naught, that is energy per bit to noise ratio. Energy bit to noise ratio increases as the level of modulation increases. So as the separation between the neighboring symbols decrease, EBA naught is increasing, so as the probability of error. So for uh, BPSK and QPSK, bit error rate is 10 power minus 3, that is 1 over 1000. That means 1 bit in 1000 bits, and 10 power minus 2, that is 1 bit in 100 bits, and 10 power minus 1, that is 1 bit in every 10 bits. So that will be the high bit error rate. So as the number of levels increase, the bit error rate also increases, so as the EBN naught. So PSK has limitations. So after 32 level, we cannot have, because the separation between the symbols will be very narrow. 32 has 11.5. So if you go to 64, it will be half of 11.5. Then we have QAM error performance. For a large number of signal points, that is AIM array system greater than 4, QAM outperforms PSK. So if you compare QAM and 4 PSK or QPSK, QAM has better performance. This is because the distance between the signaling points in a PSK system is smaller than the distance between points in a comparable QAM system. The general expression for the distance between adjacent signal points for a QAM system with L levels on each axis is square root 2 over L minus 1 into D, where D is error distance that we are calculating. L is the number of levels on each axis, and D is the peak signal amplitude. So in comparing equation 49 to equation 41, it can be seen that QAM systems have an advantage over PSK system with the same peak signal power level. The general expression for the bit error probability of an L level QAM system is given by 52, where this ERFCZ is the complementary function given by this expression Z is equal to square root log of 2L, L minus 1, and square root EBA naught. And it can be seen in figure 49. That is QAM. You can see if you compare this graph with the graph of the PSK, you will find that QAM has better uh, probability of error and EBA naught performance than the PSK. So table 4 is the minimum carrier to noise power ratio and energy per bit to noise power density ratio required for a probability of error. 10 power minus 6 for several PSK and QM modulation schemes. So bit error rate is fixed at 10 power minus 6. And for different modulation techniques, carrier to noise ratio required is listed and against the EBA naught ratio. So you can see here QPSK and QAM both has the same EBA naught ratio. When we have bit error rate fixed as 10 power minus 6. BPSK has some less carrier to noise ratio, but it has same energy bit to noise ratio. Then it increases 18.3 dB, 14.5 to 18.8 when we have 64 QM, and carrier to noise ratio is 26.6 when we set at 1 bit in error for 10 power 6 bits. Will be like 1 lakh bits, 1 bit in 1 lakh. Then we have example 17 that says which system requires the highest EBNR ratio for a probability of error 10 power minus 6, a 4-level QAM system or an 8 PSK system. That you can also tell from the table, but you can also calculate that as well. So 10 power minus 6 is fixed. Which system requires the highest EBNR? Let's see 8 PSKR QAM. So here it is for 8 uh, QAM, and this is QAM and 8 PSK. QAM 13.6 and 10 power 10.6, whereas 8 PSK need 14 dB compared to 10.6 dB. So QAM require less EBNR compared to 8 PSK. So that concludes this lecture and the modulation section. After this, we have this coding section. If you have any questions up to this point, you can ask. Next, we will start this coding section.